Welcome to Chemistry Module 16, Part 2, the final video for chemistry class. Then you are done. As usual, any questions or concerns, send them to Mr. C at mrcscience.com. Just as a note, you're coming up to the end, so the rest of the homework is going to be due. And remember, you got those quarterly tests if you want to do those as well and turn those in. Okay, so let's move on. Last video we talked about redox reactions, reduction oxidation reactions. Well, now we're going to put them into use and see how batteries really work. As usual, if you have your books handy, you should have them around. We're going to be working on page 571 if my drawings aren't up to par here. So, okay. So what they start with is they start with a simple reaction. We got copper aqueous, which is a +2, plus a zinc solid, gives us zinc 2 plus aqueous plus copper solid. Okay, basically what this says is they take a solution of copper ions +2, they drop a piece of zinc in there, solid, and you're going to end up with zinc +2 ions, and you're going to precipitate out copper. So this is a redox reaction. So if we look right here, when we have just a atom all by itself, its oxidation number is its charge. So we've got an oxidation number of +2 here, we've got an oxidation number of 0 there, an oxidation number of +2 here, an oxidation number of 0 there. So what was reduced? What does reduce mean again? Reduce means that it gains electrons, right? So in order for it to gain electrons, it had to go from a plus to 0. So copper here was reduced. Oxidized means loss of electrons. Zinc from a 0 to a +2, so it had to lose 2 negatives, so zinc was oxidized. Okay, so what they do then is they say, hey, what if we separate this out a little bit? So here I'm going to, oops, wrong one. I made a little container for us to use here because it probably looks better than anything I draw by hand. Okay, so if we got our container here, and in it is a solution of copper. Okay, if we drop a piece of zinc down here, this reaction is going to occur. Now what really happens here is electrons are transferred from the zinc. So if we got electrons in here, they're transferred from the zinc to the copper. So if we can capture this transfer, we can make ourselves a battery. So what they're saying is a couple things can happen. So if we instead do 2 containers, let's grab their containers. Got to get better at grabbing stuff. I missed it again. One last try. There we go. So if we have 2 containers, I think, yep. I can't grab anything with this. Too small. There we go. We have 2 containers. Okay, so one has our copper solution in it, Cu2 plus, and one's got a piece of zinc. Nothing's going to happen. But it says if you take a wire, some kind of conductor like copper, and you attach it to the zinc, you are going to get a reaction. You're going to get some electrons flowing from the zinc to the copper. But what's going to happen as those electrons flow, the electrons here are going to start giving this more of a negative charge. So you're going to start to cancel out some of the positive, you're going to get more of a negative charge, and quickly that flow of electrons is going to stop. The reaction will not go very far. And you can speed up the reaction even faster because zinc 2 ions need water to go into. So Actually, that won't really do much at all, but if we put water in here, then the zinc 2 ions will flow out of here, the electrons will flow there, and this will gain an overall positive charge, which will attract those electrons, and this will give an overall negative charge, which will repel the electrons, and it will stop. So how do we fix that? Back up a little bit. There we go. So we've got our conductor in here. We're going to put our aqueous solution in here, water. And so they're saying, well, first of all, they say if we drop an electrode in here, it'll help. So the electrode can be anything. In this case, it's copper. It'll help matters along. But that bonus is going to happen. Let's redraw this a little bit. Here, let's do this. Delete, delete, delete. Oops. Control Z. Too much. Okay. Okay, so let's draw this a little better now. So we got our copper ion solution. We got our aqueous with our zinc down here. And what they'll often do instead of doing that is they will put in an electrode of zinc. So we got a zinc piece here. And they'll throw another electrode in here to give it more surface area to run over. In this case, our electrode's going to be copper. They'll put a wire from one electrode to the other, and you're going to start getting your electrons to flow until those charges build up. So how do you stop the charges from building up? Well, the only charges that flow this way across conductors are negative charges because they're electrons. You can't get protons to flow the other direction because that's the center of the atom. So instead what they do is they add what's called a salt bridge. This is a really poorly drawn salt bridge. You'll see a better one in your book. But in here is salt, and we know that salts are ionic. So that means they have positive and negative ions built up inside that salt bridge. So what happens is the electrons flow here, you get the negative ions building up here, but then those positive ions those ions travel back across, and you get a complete flow. Let's see, if you go ahead and turn to page 572, you see a better picture of this. So, since the electrons flow out of here, this is the negative terminal. Since the electrons flow into here, this is the positive terminal. We have names for these. Negative terminals are called anodes. And these electrons are called anions, or anions in here, the negative charges. Okay, then on this side you have your cathode with your positive cations. Okay, this is called a galvanic cell. Let's make sure I spell it right. Yep. It was discovered by a guy named Luigi Galvani. And basically what he discovered is two different types of metal will exchange electrons. They will generate a charge. This charge can often come into contact, if you put two metals next to each other, they will corrode. And that's just that charge passing back and forth, causing some chemical reactions with the metals and causing corrosion in the presence of oxygen. So, go ahead and turn to page 574. You see it all laid out here. So you got your electron flow, you got your cathode with your positive, you got your anode with your negative. You're going to be asked to draw out some of these battery types here. This is a simple wet cell battery. it is not rechargeable. It means you can't zip it around the other way and replate or put the zinc back, because what's going to happen is the zinc will eventually be eaten off and all becomes zinc 2 ions. The copper will, now if you just ran it regularly, the copper would precipitate, but primarily the copper will plate onto your cathode or your electrode right here. So your copper ions will go onto there. So, and it will run. Cell will run until it runs out of one of its reactants, out of its copper ions or out of its zinc. So cell won't run forever. Okay, so let's take a look at how they set up some cells here. So on page 575, they have another reaction here. They use silver. Can you guess why we don't use silver in batteries? Because it's expensive. Okay, it has a positive charge, it's aqueous. So we have silver ions in solution, and we use magnesium as a solid. And it will precipitate out silver or coat it onto the electrode. And you will get magnesium ions in an aqueous solution on the other side. So if we draw out our two, let's see if I can do a better job of grabbing it. First try, look at that. So if we do our two containers, okay. In the one container, we're going to start with our silver ions, and the other container we're going to put an electrode of magnesium. On this one, we're going to put an electrode. Again, it doesn't really matter what the electrode is. In fact, there's a process that will do something like this we'll talk about in a little bit. Okay, so let's see where the electrons come from. So this has an oxidation number of, remember it's all by itself, so this charge has got an oxidation number of +1. Magnesium, 0. Now the silver becomes 0 and the magnesium becomes +2. So for the silver to go from +1 to 0, what had to happen? It had to gain a -1 charge to cancel it out. For the magnesium to go to 0 to +2, what had to happen? It has to lose 2 negative charges to get that +2. So the electrons flow out of the magnesium and end up in the silver. So that means our electron flow is going to be this direction. Okay, this is also going to be an aqueous solution because that solution is going to end up having Mg2+ in it once it goes on. Okay, then we need our salt bridge. With our positive and negative ions in it to allow ion transfer, because otherwise a negative charge will build up here, positive charge will build up here, and so we have to allow ion transfer to even that charge out to allow it to continue to flow. Okay. So because the electrons flow out of this is the negative side or the anode. Because the charges flow into here, this is the positive side or the cathode. Now what's kind of interesting about this reaction is silver is going to become, I forgot to put a solid here. Silver is going to become solid. What's going to happen is the silver is going to plate onto this electrode. So if you put something in there you want to plate silver on, this is called electroplating. And that's how they plate silver or chrome or other things onto objects. So electroplating. So does that make some sense? Hopefully it does. So that's kind of how you lay out a galvanic cell. So let's move on to a different type of cell, what they call real batteries, because you don't see batteries like this. All those liquids take a lot of space and are hard to work with. Next battery we work with, though, does have liquids. Real batteries, it's on page 579, is a lead acid car battery. So we're going to look at a lead acid battery. Now lead is Pb. The acid we're going to use here is sulfuric acid, H2SO4. So if you look at the reaction, it's kind of an interesting one. We start with PbO2, which is a solid. And we're going to use Pb, just lead, which is a solid. And we're going to put both of those in a sulfuric acid, two sulfuric acids, aqueous solution. That is going to cause a redox reaction where we get two lead sulfates, and that will be solid, and two waters, liquid. Okay, so if we look at oxidation numbers here, let's start with the basics. Oxygen we know is a -2. So if we got two of them, that means lead here has to be what? -2 plus -2, -4, so lead has to be a +4. Lead all by itself. When it's all by itself, you look at the charge of the atom. So this one is a 0. Okay. Hydrogen, except when combined with a metal, is always a +1. It always gives away its one lone proton, or electron. Oxygen is always a -2. So if we look here, we got 4 oxygens, that's -8. We got 2 hydrogens. I'm looking at this 2, not the stoichiometric 2. So we got +2, -8 plus 2 leaves -6, so we need a +6 to counteract the rest of that negative charge. Okay, let's go down here. This one's a little tricky, and they say it's beyond the book, so I'm going to show you what it's going to be. You got -8 here. Sulfur is going to stay at a +6, and we won't get into the reasons there. But now if we look 8, 6, that means the lead's oxidation number has to be +2 to counteract, because we got -8 here, +6, +2. Water, -1, -2. So if we look at the oxygens, -2, -2, -2, -2, nothing happened with the oxidation numbers in oxygen. Okay, if we look at the hydrogens, +1, or sorry, that should be a +1. +1, +1, nothing happened there. Look at the sulfurs, +6, +6, nothing happened there. So really all that changed was the lead in the PbO2 went from +4 to +2, and the lead by itself went from 0 to +2. So this is a really interesting reaction, because what is reduced and what is oxidized? Well, reduced means that it lost or gained electrons. So if we go from +4 to +2, it had to gain 2 electrons, so lead was reduced. Oxidized means loss of electrons. Solid lead went from 0 to +2, had to lose 2 electrons, so lead is both oxidized and reduced in this reaction. Kind of interesting. So, so they talk about that. So if you look on there, they have a plate with PbO2 on it, a plate with just lead on it, and then that's lowered into a sulfuric acid bath. So where is the salt bridge? Well, the salt bridge is the H2SO4, because if we look at the way we break down that sulfuric acid and water, SO4, oops, that's aqueous. So to be aqueous, we have to add it to water. H2O liquid, and we get acids are what? Acids are proton or hydrogen donors. So what's going to happen is our H2SO4 is going to lose one of its hydrogens, become HSO4. It's going to leave behind that electron, so it's going to gain a -1 charge, or just a negative charge. Water then is going to gain the extra hydrogen, but not the extra electron. It's going to get a positive charge. So this is our negative ion and our positive ion for our salt bridge in the middle. So that's how that works. This is called a wet cell. So now let's talk about batteries you're relatively familiar with, AAA, AA, things like that. These batteries are not aqueous. They don't have a liquid form in it. So they are called dry cells. Oh, by the way, we should mention that, let's scroll back up. This reaction, this battery, is rechargeable. In fact, we recharge it all the time. What you do is you use it, use the potential in the battery to start your car, and then while your battery's running, or while your car is running, the alternator recharges, so it reverses this reaction by creating electric force to push it backwards and kind of reset it. So it is reversible. It doesn't stay reversible forever. Eventually things wear out, but for quite a while it remains reversible. Dry cells, on the other hand, are not reversible. They do not recharge. Some of our dry cells are called alkaline. If you understand alkaline, alkaline is another name for base. And the reason they're called alkaline is because they use, I think it's potassium hydroxide, yeah, KOH as the base in the reaction. Instead of sulfuric acid up here as our salt bridge, KOH becomes a salt bridge, although it's a solid salt bridge. So we're not getting too deep into what happens here, but batteries, they use magnesium dioxide. Here, let's scroll down. Or not magnesium, manganese dioxide. And as the cathode, so that means the plus. And the anode will be dimanganese trioxide. Is a negative, so what happens is it's converted. And if we look here, we got a negative 2 of them, negative 4. Manganese here has to be a plus 4. If we look here, we got 3, so negative 2, so we got negative 6, but only 2 there. It has to become a plus 3. So in order to go from here to here, it has to gain an electron. So you see your oxidation changes there. Okay, so basically dry cells cannot be recharged though because it breaks down the manganese dioxide and becomes manganese trioxide or vice versa. Okay, last one they talk about is corrosion. Corrosion is kind of like this. Corrosion they show here, say we take 2 irons, solid, and we introduce it to water. Everyone knows what happens when water comes in contact with iron over long periods of time. It rusts. It gives off oxygen and also, kind of interesting, heat. This is an exothermic reaction. And this is not rust yet. Iron hydroxide. Solid. So this iron hydroxide further reacts with oxygen, and that's where we get our rust, which is Fe2O3. So it's kind of a dual reaction. This is kind of an intermediary reaction, but this is corrosion. This is a little bit different than corrosion I was talking to you before, where if you bring 2 different metals together, because of that change in oxidation numbers, it tends to corrode. It tends to react. Okay, this is the final video for you for this chemistry class. So once you have done that and finished your tests, you have completed chemistry. Again, if you have any questions, contact me at Mr. C at MrCScience.com. Thanks.